So, what this allows us to go ahead and start doing is to look at the evolutionary behavior of the object's velocity in equal intervals of time, or in multiplicative intervals of time. So we can look at t is equal to 1 tau. One time constant goes by, where the time constant itself is defined by m over b. So after one time constant, we've got that v of t is equal to tau is equal to v sub t times 1 minus e to the negative 1. That's just a number. What we end up getting by defining this time constant is percentages of the maximum speed that are obtained after certain intervals of time. 1 minus e to the negative 1, this is going to be equal to 0.632. So we get 0.632 times v sub t, which then says after one time constant, the object will have 63.2% of the maximum speed that it can obtain. 63.2% of v sub t. Well, we can look at two time constants. We're going to have that v of t is equal to 2 tau is then equal to v sub t times 1 minus e to the negative 2. This again, that's just a number. This ends up being 0.865, and we get ourselves 0.865 v sub t, which says after two time constants, we're at 86.5% of v sub t. We can keep going with this. Look at three time constants. For v is equal to 3 tau, what are we going to get? We're going to get 1 minus e to the negative 3, which comes out to be 0.950. So we've got ourselves the v of t is equal to 3 tau, gives us 0.950 v sub t, or 95% of the maximum speed. So what we can see here is that there's kind of this set in stone way of the evolution of the object's velocity in terms of how it behaves. One time constant, got over half of the maximum speed is obtained, but then it starts to sort of slow down in terms of the rate that it's changing at. Why? Well, it starts to slow down because the faster it's going, the greater the resistive force. The greater the resistive force, the less the acceleration is. Until a point in time in which the resistive force is equal to the gravitational force in the opposite direction, at which time the object has no more acceleration because the net force is equal to 0, at which time the object's velocity is that of the terminal speed, v sub t. Anyway, I'm going to write down a couple more. Take this up to 5. Go t is equal to 4 tau. We get that v of t is equal to 4 tau is equal to, oops, calculate this one out. We've got 1 minus e to the negative 4. Gives us 0.982, we'll call it. 0.982 v sub t. And then t is equal to 5 tau. V of t is equal to 5 tau is equal to, let's change that over to a 5 there. We get ourselves 99 or 0.993, 0.993 v sub t. One more. T is equal to 10 tau. 10 time constants go by. V of t is equal to 10 tau is equal to 0.99995 v sub t. 99.995% of the maximum speed is obtained after 10 time constants. We take this to be approximately v sub t. That is, the general rule is after 10 time constants have gone by, the object can be assumed to be at its terminal speed itself. So, there we go. What we want to do with this is actually see a nice little graphical representation of all this and understand why we were looking at things in terms of this time constant. So, the main thing is because we're looking at equal intervals in time. 1 time constant, 2 time constants. Well, the time constant itself is just some amount of time that is determined by the mass of the object and the coefficient of proportionality between the resistive force and the velocity vector. So let's do this. Get a nice little graph here. Here's time, and then this is going to be velocity as a function of time. We have some terminal velocity, which is going to be something like that. And then we can start to take some other little points and start mapping stuff out. So we've got right there, that'd be about 0.5 of v sub t. And then we've got 0.632. This is kind of estimating around, but 5, 6, 3, 2, 0.632. Then we got 86.5. We can call that 75, 86.5 somewhere up here. 0.865. And somewhere up here we've got ourselves 95, or 0.95, and so on. That's good. And then we can start to write out some taus. Say that that's a 1 tau. Come over another equal amount of that. And that's a 2 tau over another equal amount. 3 tau. 4 tau, and so on and so on. And then we can go ahead and say, we've got these points here. After 1 time constant, we are at 63.2% of the maximum speed, which gives us a nice point right there. We've got another one. After 2 time constants, we're at about 86.5%. 3 time constants, we're at about 95%. And then as time continues to go on, we get closer and closer to that true value there. I'll just plot out those 3 and get the picture here. So, start at 0. Whoosh. And not the prettiest picture. I'm gonna cheat a little bit. There we go. This is the curve that represents how the object's velocity changes with respect to time. And again, in that first 1 time constant, that's where there's the biggest change. And as time goes on, that change flattens out as it approaches its maximum value until the velocity is constant. Acceleration 0, that's what we got. So that is what we have regarding our velocity-dependent forces, or a resistive force that is proportional to the object's velocity itself. What else could we do? We do some problems. So let us go ahead and do that.